Hello, I'm Katie, and I'm going to be going over something called self-calibration. So previously, in your other lectures, you've been taught all about the visibility and how to calibrate your data. In my last lecture to you, we discussed how to turn your visibilities into an image by using a Fourier transform in CASA. You've made an image and you've done really well at calibrating and making the image, but you still may not have the best image you can get though. Early calibration steps may alleviate some of the errors introduced during the observation, but it can never remove all of the variations across the data. Errors in your image may scatter the power, and for bright sources, this might not be too noticeable. But when you have areas of weaker emission, this will be greatly affected and lead to more errors in the map. Self-calibration is a technique that we can use to further reduce variations in the data by having a target use itself as an amplitude and phase calibrator. So then we can use this process to perfect our image just a bit more. To understand self-calibration, it's important that we understand calibration in general. So I know you've gone over calibration previously, but we're going to do a recap. Radio telescopes are not perfect. They have errors, and many errors are introduced to the data, whether it's through receiver noise, result of atmospheric conditions, or even introduced through radio frequency interference, which is RFI. In any case, the errors need correcting for, or at least minimizing. And when calibrating your data, you must apply your instrumental corrections. This could be correcting for the system temperature. Often this is done through the observatory pipeline. You need to edit the data. So remove your bad data, and we call this flagging. So look for unusually low points, dropouts, or bright spikes caused by RFI. Then you need to apply a bandpass correction. So here in the corner is an example of bandpass calibration on the right. The plot shows amplitude versus frequency. So in the top plot, you can see uncorrected data. The data has some strange pattern to it across each spectral window. So this is our instrumental effect. And the bandpass pattern is not expected to change very much in time. So over the course of the observation and throughout your observation of each calibrator and target, we can assume it to be a constant. The bandpass is adjusted, and we use a complex correction to fit to your data so that you get a straight pattern across the frequency when you plot the corrected data. As I said, this won't change during your observation. So one bandpass is all you need typically. During calibration, you've also applied corrections to phase and amplitude. So the amplitude has long time scale changes, typically in hours or so, but you can get short time scale changes between each of the scans. You also get phase changes on short and long time scales. So you will need to apply these corrections for those. There are also frequency dependent phase delays that have been corrected. So once you have found the corrections using the calibrators, you can apply these same corrections to your target. So the phase calibrator is close enough to the target so that we can assume the conditions are the same, but assumptions rarely lead to perfect results, as we will see. So I've sort of touched on this a bit, but phase referencing is how data is calibrated. You observe a source and you collect data on two calibrators, at least two calibrators, during the observation. The first calibrator is the flux calibrator. You observe a bright source That is a source that is well above the noise limit. And this source has a well-known position. And you can sometimes get away with a slightly resolved source, but you really need to have a source where you have a well-known structure, so you have a good model for it. So again, the flux is not expected to vary much during the observation. So the flux calibrator does not require constant monitoring. A couple of scans of the source is enough, typically. The phase calibrator is different though. The phase calibrator is a source closer to the target. The idea is that large fluctuations within a few degrees can occur throughout an observation. So the phase calibrator will need to be observed alternating with the target every few minutes so that these variations can be corrected. Of course, this is not a perfect process. Although the phase calibrator and the target are close, they are not in the exact same spot, nor are they observed at the exact same time. So in particular, you can have changes in the atmosphere locations of this target and the phase calibrator. So you can have changes in water vapor content. Some air may be drier, some air may be more humid in certain parts. At low frequencies, you need to consider the effects of the ionosphere, whereas at high frequencies, you should consider the water vapor absorption and scattering of your emission. So there are many other effects that contribute to calibration errors as well. For antenna-based errors, there is something called radio seeing. So this is the same problem that optical astronomy has. So turbulence in the atmosphere tends to cause this kind of blurring or what we call twinkling of astronomical objects. It's the same with the radio spectrum. Atmospheric attenuation can reduce the amount of radiation that reaches the array due to absorption and scattering by the Earth's atmosphere. And you can have variable pointing offsets, where the telescopes are told to point in the same position, but again, they will not be perfect, so there may be some offset. You can have offsets in delay or changes in gain, delay, or phase. For baseline-based errors, you can have problems with the correlator, you can get interference signals or noise from the radiometer. You might think, so what if there's errors in the image? Can it really affect the image or even the science? The answer, of course, is yes. If you introduce excessive phase errors, you'll have a slight offset between where the source is at different times. This means your image isn't exactly aligned, and so the flux measurements will be degraded. If you decrease the flux measurements, you'll have difficulty identifying emission that was already weak to begin with. You'll also have higher noise and smeared emission. You'll notice antisymmetric effects around the field. If you have amplitude errors in your image, you can still have a higher noise measurement, and you can still have reduced flux for your source. You'll notice amplitude errors by the presence of symmetric artifacts. Sometimes it can be stripy, but not all stripes are amplitude errors. So if you have symmetric lines, it's more than likely an amplitude error. But if you have a random line that's streaking across your field, it could just be that's RFI sneaking its way into your field. And so you have to go back and do a little bit of editing by flagging these breakpoints. So again, just to show you an example of an image without going through the steps of calibration. On the left, you have an image calibrated with phase referencing only. In the image, you can see some antisymmetric errors dominating the image. The noise is not Gaussian-like. Without knowing what the numbers in the image are, like the RMS noise, you can still look at it and notice it isn't as nice as you would hope it would be. So the image on the right has been calibrated using self-calibration to correct the phase. This is just a phase self-calibration. So the errors that are in the left of on the left image are symmetric. So when you only have symmetric errors left, you know you are done with phase self-calibration and you can move on to correcting amplitude and phase. So the point I've been trying to make through these slides is that self-calibration is just calibration. We use the same tests in CASA, like Gainful and ApplyCal, and are still correcting the phase and amplitude. The only difference is we are using the target to calibrate itself. So think back to the visibility equation. You've probably seen this equation so many times during this training. So you have an equation that shows the observed visibilities, and you can show that it's made up of a bunch of terms multiplied by the true visibilities. So this top equation, our observed visibilities, a bunch of terms multiplied by true visibilities. So one term that we want to focus on is the complex gain of each baseline, which is our GIJ term. This term can vary throughout the observation, so it's important to correct it as much as we can. Self-calibration is not something that we can do on every single object. So there are a few conditions we have to meet before we can consider self-calibrating. First, you need to consider your signal to noise for the array. We've discussed signal noise formula in the imaging lectures, so I won't go into the full details about it. But if you have calculated the theoretical noise and are finding that your image has a significant amount more than that number, your noise is much higher than that number, you probably could use a bit of self-calibration. If you're slightly above the theoretical noise limit, then you're probably okay. You're likely never going to reach the noise limit for various reasons. So it's okay if you're not exactly there. So say you calculated your noise and your image now is very high compared to what you're getting. Can you then self-calibrate? Sadly, no. You still need to have a bright target. Unfortunately, there isn't one set that defines bright, one set number that defines bright, I guess. You need to know your signal to noise and what is appropriate for the number of antennas in your array. The good thing about self-calibration is that it does not care if your source is resolved, and it doesn't care if there's weak emission in the field, as long as you have a bright peak, a high signal to noise, and a high RMS. Self-calibration could work for your image. The self-calibration process is simple. Thankfully, there aren't many complicated steps to follow. So you could start by creating a source model. You need the model so that you know where the source is and what the shape of the source is. The model is typically produced when you create the image. So it's a good idea to check if the model has been properly put in the model column of the measurement set. So you can check that with your plot MS tool. And if it's not there, it's okay, you can manually put it in later. But for now, we're going to assume that we did everything correct and our model is in the model column. So now you run your Gainful to find the antenna gains. And the Gainful uses a least squares fit to the visibility data to find the corrections. And once Gainful finds the corrections, you can use ApplyCal to apply them to the observed visibilities. So now that you've corrected visibilities, you can produce another image and see whether your image has improved at all. If it has, repeat the process until your image is no longer improving. That's usually the safest way. For self-calibration, you should start with only phase calibration. Remember that problems you get the problems you get when you have phase errors. Well, we need the phase to be as good as we can get it so that our amplitudes align and they're not degraded. Once the phase errors are gone, then we can move on to amplitude and phase calibration. So now how can we use these steps to self-calibrate in CASA? First, you image the visibilities using the imaging tasks. So these are either T-clean or clean. So while imaging, you can make a box around the brightest emission, and that will help you speed up the process. So for your first image, it's a good idea to not clean too deeply. You don't want to start adding structure that you're not sure if it's even real, because you could be introducing it into the model and then it becomes frozen there. So you want to make sure that you have a parameter. You have the parameter view scratch set to true. If you forget or if the model did not properly add to the model column, then don't worry. You can use the task FT to Fourier transform the clean components in. And that's done after you've imaged. So you can check your model and compare the visibilities with the task plot MS. So on the right, we have an example of the first image and the first clean image, a source 3C277.1. If everything looks okay, we can move on to finding the gain corrections with the task gain cal. So the first part of self-calibration is going to be just phase. So we set the cal mode to equal P. P for phase. So here is an example of the product of gain cal. It's the phase solutions for a target. On the left side, we have the phase for the target using only the phase referencing. On the right side is the same target and that we've done phase self-calibration on. So you can see that the phases are smoother on the right and the offset between the different polarizations has gone away. So once you have solutions, you can apply the corrections using the task apply cal. Then you make a new image and model and repeat the process until you are satisfied with the results. So these are based on the conditions. If the phase errors appear to be gone, your noise has decreased, then it's probably time to go to amplitude and phase. So to do amplitude and phase calibration, you should set cal mode to AP instead. So to summarize the self-calibration process, you initialize an image, you do an initial image, you do phase self-calibration, you do a shallow clean image, and then you do phase self-calibration, then you do a deep clean, and then you do your amplitude and phase self-calibrations, and then another deep clean. Then you've completed all the steps and you should have a beautiful radio image. There isn't, I should stress, there isn't a set number of phase and amplitude calibrations. If your source is very complicated, you may need a couple rounds depending on the problems you're having with the source. So you can see a big difference between the first image on the left and the final cleaned image on the right. So the artifacts that are all over the first image are gone, and you're left with Gaussian-like noise. And all of these ripples are minimized. or gone. Self-calibration can help us clean up the image quite well, but there are some limitations to what it actually can do or what it can fix. To start, there is no fixing bad data. Bad data will still be there, and that needs to be flagged. You can't add flux where there's no data to begin with. This is another problem. So this is the problem of something called missing short spacings. So you can, if you don't have the short spacings, a negative bowl where there's no flux can develop in the image. To fix this, you need data from compact arrays. There's also baseline dependent errors. Those errors may need another test called BLCal because it's not part of the self-calibration method. BLCal solves for baseline dependent errors. Also, you can't fix pointing errors, variability in source, and weird delays in the data, among other things. So of course, there are many options to choose from that we have not even discussed. For the process we discussed throughout the lecture, we found solutions using the clean components in the image. You could also use a point source. You could fit a Gaussian to a slightly resolved source, or you could fit a model to the UV plane. Often the easiest is to use the model from your image, which is the process we discussed. Baseline, you have some baseline options as well. If you have a simple source that maybe isn't resolved, you can use all baselines. When you start to get more complex structures, it might be necessary to use the longer baselines. The solution interval, we didn't discuss that very much. So the solution interval should also be chosen carefully. You want to choose a solution interval that gives the best signal to noise. So look at plot MS and see if there's a meaningful pattern in the phase versus time. You want it to be short enough that it can sample phase errors. So it's best to start off with something longer, like maybe the scan length. And once you get a perfect model, move down from there. And finally, I will leave you this list that has a few sources that will be excellent supplemental material to this lecture. Because self-calibration is an important tool and it's very useful, but it's difficult to get into all the details in a short lecture. So I highly recommend any of these, and good luck with your self-calibration.